So potentiometer is the device which we have to finish today. So what is this device, what it does, and why we use this device? So first of all, it is a device which is used to measure what? Any idea? What we measure using this device?
Potential.
Not potential. For potential, we have voltmeter, right?
Yes.
So this does something different. It measures the EMF of a cell and its internal resistance. And the next question is on what principle it is based on? Let's say we have studied that meter bridge is based on balanced Wheatstone bridge. So similarly, on which principle potentiometer works, or it is based on? Any guess? So potentiometer is based on what? You can guess. Actually, this is not required. I mean, you're not supposed to know, but at least you can guess. Okay, let me give you the option. Balanced Wheatstone bridge, A, option A. Option B, magnetic effect of current. C, Kirchhoff's voltage law, Kirchhoff's current law, Ohm's law, and yeah, that's it. So which law it is based on? Can you guess?
Ohm's law.
That's correct answer. So this law is actually based on Ohm's law. So it is based on Ohm's law. So how this device actually works? So what is the working? I mean, what is the construction of the device, and how we actually use it to find the EMF of a cell as well as its internal resistance? So every potentiometer will have two circuits basically. So every potentiometer will have two circuits. The one is called driving circuit, and the other part is called potentiometer wire. Similar to the meter wire in case of meter bridge. In meter bridge, the condition was that the wire length must be 1 meter, but there is no such restriction in potentiometer. Potentiometer wire can be of any length. It could be less than 1 meter. It could be more than 1 meter. It could be 1 meter as well. But looking at the practical consideration, length of potentiometer wire is generally, I mean, I'm saying about the practical aspect, taken from 4 meter up to 17 meter. So in actual lab, when we try to create this device, the potentiometer wire is taken up to this much value, depending on the lab size and the size of the bench. So potentiometer wire is generally fitted on a bench, and the bench is put in one corner of the lab. So earlier we used to have the wooden bench, and on this wooden bench you can see there is a wire, put, and the weight is put is something like this. So we have some metallic strip where you draw the wire. Then you can keep this length up to either 1 meter or 2 meter, again, depending on the bench size. Like in my college, when I was pursuing, it was 2 meter long. In a school lab, I have seen it's 1 meter itself. And you can make any number of turns. I have less space, so I'll stop here. So the orange part is basically the thick metallic strip. And you will have some meter scale also attached to the bench so that you can read it accordingly. So they put the calibration on the table itself, which is easier to read. The driving circuit will have something called a cell called driving cell. So the driving cell will have a value which is typically more than the EMF to be measured. So let's say if you wish to measure EMF of value 1.5 volt, so you will keep your driving cell more than 1.5. So generally driving circuit, driving circuit will have a driving cell. And the EMF of this driving cell is going to be more than, in fact, much more than any of the EMF of the cell to be measured. This is the first thing we need to know. So generally what we do in lab, we go to the lab instructor, we ask for give me a cell. So they will provide you some lead accumulator cell. It's like a cylindrical cell you might have seen. And you bring that cell to the table, which is the potentiometer wire table, and you make the connection using connecting wires. Apart from the cell, we need to have something called rheostat. So the way we represent the rheostat is by drawing a line like this. So it will have some length actually. So have you seen the rheostat, anyone?
Yes, sir.
Okay. So in a rheostat, okay, if you have not seen, just Google it quickly and see it for yourself. This is the circuit diagram of rheostat, which I'm going to go. And this is called jockey, which is like a slider. And if I take the entire length as L and the total resistance as capital R, and if you put the jockey up to here, let's call X distance away from the left hand. So circuit will only take, because see the circuit, if you complete the circuit, this part will have nothing. This is open to the circuit. So we consider only that resistance which is part of the circuit. And if you try to calculate R as a function of X, you can add R upon L into X, right? So this is called the rheostat, which is a variable resistor. And which is a variable resistor. And the purpose is to alter the resistance in a circuit. So if X is 0, a rheostat will offer you how much resistance? How much?
0.
0. And if X is L,
R.
it will offer you full resistance R, correct? Now this is the prerequisite. Beyond this, if you can connect anything else for your own convenience, let's say a meter to measure the current flow. Okay, that is extra. So this is our driving circuit, and this circuit we eventually connect to this potentiometer wire. So this is the left end, and let me change it. So this is left end, let's call O. This is right end, let's call A. So this is A will connect here and O will connect here. Understood? So the simplified version that we draw in order to solve any question of potentiometer is this. So what we exactly draw is driving cell, a bigger value of cell. We just show R. So you can derive R in terms of X and L, but the net value we call R itself. So if they mention that rheostat having such and such resistance and jockey is at that particular location, the length of the rheostat is given to you. In that case, you have to use the R by L into X formula. Otherwise, they give R directly in most of the scenario. So this is the part which you can draw. And no matter how big the potentiometer wire is, you simply connect the two ends, and this is the entire potentiometer wire of total length RL and total resistance, let's call R naught. So this is your simplified diagram. So this is really simple, right? You can further draw this as like this. So I think it is very easy for all of you to calculate the current in this circuit, right? What will be the current in this circuit? I equals to
E divided by R plus R.
E
R
divided by
plus
R plus
R no.
R naught. So that's pretty easy. So in terms of circuit, it is really easy, but in terms of application, it is bit tedious. So we'll see why it is called tedious. So you have to be very careful in terms of the operation, like how it works exactly. So once you have the circuit, we need to define something called resistance gradient. So we have defined this before. Now we'll define it again. Let's call L naught. That's better way of writing. R naught, L naught. Yeah. So we can add this is R naught upon L naught, which is resistance per unit length of potentiometer wire. So this wire O to A is called now. If you remember the cell, real cell, okay, with E as EMF and R as the internal resistance. There are two cases. Either it could be charging or it could be discharging, right?
Yes.
So in case of discharging, if current is like this, we know that the potential across will be how much? E minus IR.
Yes.
And in case of charging, it will be
E plus R.
E plus IR, right? Very good. So the potential across this could be either E plus IR or E minus IR. But what we are looking for is E, right? What we are looking for?
E.
Only E. We don't want V. In terms of measurement, we can measure V actually, but we are looking for E. So that is only possible when. So for V equals to E implies I must be 0, correct? So the moment you make current 0, the potential across it will be same as the EMF, isn't it?
Yes.
So to calculate the EMF of a cell, we have to create a situation or circuit in which no current should pass through the cell. Just Okay. So how the calculations are made? Okay. So let's say this is the cell. You bring some cell with EMF E and internal resistance R, which can redraw as E in series with R, right? Both are same thing. I hope you remember this part.
Yes.
Yes.
So what you do exactly is you bring this cell to potentiometer circuit. And how you bring it? Let me show you.
Sorry.
So now you can see that this cell has been brought here. And now I'm going to make a connection. How we make the connection? Look at this very carefully. The first rule is the high potential of the cell must be connected to the high potential end of the circuit, which is this point. Do you realize this? So the left end of the circuit is at high potential because this is plus, this is minus. Yes or no?
Yes, sir.
Yes.
Yes, sir.
And the high potential of the cell is also left. So we connect left with left. So this is the connection you have to make it here. And this point C will slide over the potentiometer wire. So you will go to the table and you will slide the jockey over the wire. And you will keep on doing till the galvanometer shows null deflection. So when you do so, when there is no current through the galvanometer, which means there is no current through the cell, isn't it? And if there is no current through the cell, it means something really interesting. It means the current in the actual circuit coming like this, and the same current is going through the wire I. And why this is possible? Because we have chosen a point C in such a way that IG is how much?
0.
0. It means no current is getting distributed at the in the below path. The below path is currentless. So whatever current is developed or generated by the driving circuit, or sorry, you can say potentiometer circuit. So potentiometer circuit is creating current I, which is known to us. What was I? Do you remember?
E by R plus R.
R naught.
Very good. So now can we say, if I walk in this circuit, if I move in this circuit, I can write KVL, Kirchhoff's voltage law. Okay. So let's say the null point is L distance away from the O point, the 0, I mean, you can say rating point. So let me redraw this circuit in a more logical manner so that you can feel comfortable. So how we draw the circuit? So from O to C, because we have a junction, because you can see you're making a connection. So you break the point. So the O to C represents one resistor. And then C to A represents another resistance, right?
Yeah.
Yes.
And this I can say the value of resistance is K times L, and this I can say K times L naught minus L. Do you realize this? Yes or no? Because the total length is L naught and L is on the left side. This is C. So the remaining must be L naught minus L in length value.
Yes.
So the resistance offered will be K times L naught minus L. Okay. And because of the particular connection made, we also know that there is no current. There is no current through the galvanometer, right?
Yeah.
Just a minute. I have less space left. So this is your circuit E, R. But because of the null condition, if C represents the null condition, it means the current in the actual circuit will be unaffected. So although I have attached one parallel branch, it is not going to affect the entire calculation of current in the actual circuit, and the same current will follow here. Same will flow here. Is this clear? So if you write the
Yes.
KCL in the bottom circuit, the bottom loop, this loop. So how to write the answer? When you write KVL, so you can start from O to C. So O to C potential will decrease. How much? Minus IR.
Minus IRS.
What is R here?
K.
Correct. So it's
Yes.
minus IKL.
IKL.
I can write kill. It looks nice.
Yes.
So minus kill, then plus E. And because there is no current in the lower circuit, so R will affect, R will do nothing actually.
Yes.
So can we say this is equal to 0? Can we say yes or no?
Yes.
So E turns out to be kill. Oh, I wrote KLI. Okay, anyway, I can write KIL. E kill. And K is the resistance gradient. If you want to write in complete sense, K was R naught by L naught, which is constant. I was E upon R plus R naught, which is constant. L is L. Now, why we call this is based on Ohm's law? The Ohm's law says that V equals to IR. And also we know that for a wire R equals to rho into L by A. So if I make I constant, rho is constant, area of cross section of a wire is constant, then can we say V proportional to L
Yes.
for I equals to constant? So if we make sure that current in the actual circuit is not varying, not getting distributed, then potential across the potentiometer wire will be proportional to length. So potential across O to C will be proportional to L only, isn't it?
Yes.
And in fact, you can see that here the entire calculation is saying that E is proportional to L. So in various textbooks, they start with E proportional to L. They will not derive the entire formula. But you can derive it from scratch. You can derive it completely without any confusion. Is this clear?
Yes.
Yes.
Now, as you change the cell, let's say if you bring some another cell with some different EMF, the null point will shift or remain same.
Shift.
So if I increase the EMF from this value, the null point will be right of C or left of C.
Right.
So let's say instead of this
It will
cell,
be
if I,
left, right?
instead of this cell, if I bring another cell of value greater than this value,
Yes.
so my null point will be right of C or left of C. My new null point. Tell me. See, what is balancing E? KIL, that is I into the resistance up to the point C, right?
Yeah.
But I is constant, no? So when you increase the E, to balance a bigger value, we need greater length, or you can
Yeah.
say more resistance. So the new null point will be right of C or left of C.
Left.
Why left? Can you explain? You are not realizing anything. Anybody else? What will happen?
So it will be on the right because E is directly
Because,
proportional to L.
yes, so more the E, more the L. Simple. I is constant, so I into R is the potential difference.
Yes,
So
yes.
voltage across the potentiometer bar is equivalent of the potential of the EMF of the cell. The potential across O to C is representing the EMF of the cell, yes or no?
Yes.
So if you bring bigger cell, greater EMF, then to balance we need more resistance, right? More
Yes.
potential difference. So the new null point will be right of C or left of C.
Right of C.
Right.
Anyone not able to realize this? All have realized? Excellent. Archit, you understood?
Yes, sir.
Kanu?
Yes.
Okay. Shall I proceed forward? If this is clear.
Yes.
Yes, sir.
So generally, how we create a circuit is like when you perform the experiment, you need to draw the potentiometer circuit by drawing a similar diagram. E, R. Sometimes they don't write R also. It means the E is the only potential difference. Okay. Let me show you something more. So this you can redraw as nothing else. So can I redraw the circuit like this? I just pull this part here and this part here.
Yes.
Okay.
Yes.
And why I'm saying this, because we know something called voltage divider rule. So what is the maximum potential difference that can appear across R naught if I take the entire R naught? So as per the voltage divider rule, voltage is proportional to the resistance. So V1 will be R upon total into total
Into
EMF.
E.
And V2 will be how much?
R not upon total.
Which means the maximum potential that can be measured is this much only, because this is the maximum potential across potentiometer bar. And since we connect our cell across this length, so we cannot measure a cell whose EMF exceed this value. Do you realize this? Yes or no? How we are calculating the EMF by connecting that cell with the wire itself. Okay. So you're connecting one end here, other end somewhere here. So you're only taking a fraction of the total potential available. V2 is the upper limit. So C can go up to where? This end. It cannot go beyond this, yes or no?
Yes.
Yes.
Yes, sir.
So in the worst case scenario, what is the maximum EMF we can measure? V2. Do you realize this? Yes or no?
Yes.
Maximum EMF. You may get a question in which circuit will have only E, not R, and then the potentiometer wire. So in this case, can you tell me what is the maximum you can measure now? What is the maximum you can measure? What is the maximum potential difference
E.
across R naught? E. Because that is a cell directly connected across the
Yes.
potentiometer wire, so we cannot measure more than E value. So any fraction of R will be also a fraction of E. Okay. In this case, if this is L naught, then if you choose a point here, let's say this is O, this is A, this is C. If I call this is L, so what is the VOC equivalent of? So VOC will be equivalent of the L by L naught into E. Do you realize this? The fraction of length is fraction of EMF.
Yes.
Yes.
And what is VCA?
L naught by yeah.
Not mine.
Yeah.
You can see that L is taken from the positive end. So you may come across any type of circuit, one with just E, one with E and capital R. So rheostat may be on the leftmost side. Okay, so that is equivalent of rheostat at the leftmost end. X is 0, right? So if I put X equals to 0, it means if the rheostat is on the leftmost side, then the potential difference appearing across the entire potentiometer bar will be complete E. Yes or no?
Yes.
Once again, if I make X equals to 0, then the potentiometer bar will have EMF or it's a potential difference equivalent of capital E.
Yes.
So if you have realized this part, then you are done with the potentiometer. You can solve any question with ease. So generally, there are two types of questions you will come across. So let's say we have two cells, one with EMF E1, internal resistance R1, other with both are given a switch. You can say key K1, key K2. So this is the circuit given to you. I mean, the cell. And how they mention the question, they will tell you when K1 is closed, and K2 is open, then which cell will be part of circuit and which will not be part of circuit? So if you connect O to the left hand and C to the mid of the somewhere in the wire, and if I close K1 itself, not the K2, then which circuit is active, which is open, like not in part of circuit?
That
E1. If K1 is closed, then which circuit will be part of, like which cell will be part of circuit?
even
Only E1. Na?
yeah.
Yes.
E2 cannot be part of circuit
Yes.
at all.
Yeah.
So the null point obtained in such case will be corresponding to which value of EMF? So the null point
Even.
is obtained at OC equals to L1. So can we say this means therefore E1 must be proportional to L1?
Yes.
Yes or no?
Yes, sir.
Okay. So the next case is when K1 is open and K2 is closed. So when K1 is open and K2
Now
is closed,
E2.
so the null point is obtained at OC dash equals to L2. Therefore, E2 is proportional to L1, L2.
Yes.
Now the rest of the term, the I, the gradient Ki, the KIL, the Ki will be same for both. Yes or no?
Yeah.
So the actual relation will be KIL1, and the actual relation here will be KIL2. We are not supposed to write all this lengthy thing. We can just write like this. Therefore, the ratio of the two will be how much?
L1 by L2.
So given L1, given L2, given E1, can you find E2? Yes, you can find it. So out of 4 term, if 3 is known to you, you can find the remaining term, correct?
Yes.
Yes.
So now we can go to the case 3. When K1 and K2 both are closed. Now, if you remember, when you close both K1 and K2, these are cell in parallel. Do you remember this?
Yes.
And we have something called equivalent EMF, the E equivalent formula. The E equivalent formula from the Millman's theorem. And the formula is
E1 by
R1.
R1 plus E2 by R2 upon 1 by R1 plus 1.
So the null point obtained OC double dash is L3. So in this case, basically E equivalent will be proportional to L3. Do you realize this?
Yeah.
Understood. So you can have any scenario. Okay. So you can keep on writing this way. The next scenario question. So let's say we have a E2, E1, switch. Let me do a nicer. So I have 2 cells, both are in series combination. These are real cells. So now if I bring this circuit into consideration, so here I have to make some assumption first of all. Okay, I'm taking O as the high potential. So assuming the facing one, which is E2, is more than E1. So case 1, if K1 is closed and K2 is open, and if K1 is closed and K2 is open, then what we can say? And so the null point, this is a new question. Null point is obtained at OC equals to L1. What should the answer here? If null point is obtained when OC is, first of all, K1 is closed, K2 is open, it means the part of the branch which is part of circuit is the upper branch,
Yes. sir.
Yes.
and the null pointer will represent what? The equivalent of the two combination.
Yeah.
So what is the equivalent of series combination? In series combination, what is the equivalent? If the polarity is same, then it is simply sum of the EMF,
Yeah.
which you don't remember. Huh? Very good. I think we have done this in cell. So can we say E1 plus E2 is proportional to L1? Yes or no?
Yes.
Because null point is representing the net value of the O to C, and O to C will give you E1 plus E2. Case 2, if K2 is closed,
Sir,
yes,
so in this, was it necessary to give E2 greater than E1?
yeah, I'll come to that.
Okay.
That is, it is actually necessary for some reason. Okay, I'll come to that actually. If K2 is closed and K1 is open, what is the net EMF across O to C? What is equivalent now?
E1 plus E2 proportional to L2.
No. You can see closely these are having
Yeah.
opposite polarity.
That's right. Okay.
And so we take the left one as main. Like, no, the positive must be facing the positive of the actual circuit.
Yes, sir.
So the left end must be positive, which is only possible when E2 is more than E1.
Okay, that's right.
If I make E1 bigger, the net EMF becomes negative for the left end. In that case, the null point cannot be obtained. That's the whole idea. It means some current will flow. You cannot stop the current. Current will come to the path for sure. Are you getting it? What I'm saying?
Yes.
Yes, sir.
If you want, you can make a note of it. The net EMF must be positive on the left. Okay. So for null point to be obtained, the net EMF must have positive value on its left. Okay, I hope you got the idea. So in this case, E dash equivalent is how much?
E2 minus
E2
E.
minus E1.
E2 minus
So if null point is obtained at OC dash equals to L2, then E2 minus E1 must be proportional to L2. Okay.
yes.
So generally they ask you question, find the ratio of EMF of the two cell. So from here you can do the componendo, dividendo, or you can rearrange and get the ratio of EMF, which will be in the same ratio. E2 will be L1 plus L2 and E1 will be. Okay, now that's interesting. Which one is bigger, L2 or E1? L1. L1 is bigger or L2 is bigger?
Sir, I think L1 is bigger.
Correct. L1 is bigger
Yeah.
because L1 is representing sum of potential, L2 is representing difference. So it
Difference.
must be small.
Yes, sir.
So that's logical. L1 is bigger. So if you solve and get the ratio of E2 upon E1, you will get something like this. Okay. I hope this is clear.
Yes.
Yes, sir.
So how to use this circuit to find the internal resistance of a cell? So to calculate the internal resistance, we do some trick. Now, first of all, let's try to realize why we do this trick. So the driving circuit only have E and R and the potentiometer wire. And we know that current in the circuit is E by R plus R naught. And why this calculation is important, because we know that this current will not distribute. The moment current will distribute, you have to solve from the basic, like using the normal idea of circuit. So we'll come to that question as well, when the current is also flowing through the circuit. So if we have a connection like this, so we have K1, we have K2. If I close K1 and if I obtain the null point, then null point will represent what? The null point will be corresponding to which EMF?
Close K1.
Yeah, if I close case 1.
So E.
Then null point will give you the E value, correct?
Yeah.
Because the bottom branch will not be part of circuit, isn't it?
Yes.
So the EMF will be equals to KIL, right? Where L1 is null point. Yeah, L1 is null point. You can say OC is L1. But to find the internal resistance, the small r must be in some picture, no? Because unless the small r is not coming to picture, we cannot write the we cannot get the r, right? So in equation, I need to have r.
We can put the I value.
You can put the
I value.
I value, then it still could do nothing because current, there's no current in the circuit, right?
Oh, yes, yes.
R will never come into picture, whether it will do
Yes.
whatever. So to get rid of this situation, we bring something called shunt resistance again. And the moment to bring the shunt resistance, we take the scenario 2. K1 and K2 are closed. The moment to close both K1 K2, although we can still obtain the null point. Null point means what? IG is 0, correct?
Yes.
So if IG is 0, it means nothing is going this way. It means nothing is coming this way, correct? And if nothing is coming and nothing is going, then whatever is coming here will go this way. Am I right, guys?
Yes, sir.
But the moment you close both, you know what will happen? An internal current will set up in the loop itself. It means this circuit will behave as independent closed circuit. So nothing is coming. It's okay. Nothing is going this way. That's also okay. But something can flow itself, no? So current I0 can flow inside this loop itself. Will not go this way or that way. Do you realize this? What I'm saying?
Yeah. Yes, sir.
Sir, I did not get it.
So when you close K1, K2, then this is a closed path.
Hmm.
So in this closed path, current will be established. Yes or no?
Yes, sir.
So I0 is the current established, and I'm still taking IG to be 0.
Yeah.
So both situations are possible, that I0 is non-zero and IG is 0.
Yeah.
And
Yes, sir.
because there is a current, we can find the R will come into picture for sure.
Hmm.
So what is the new EMF across A and B? Let's call some name it P and Q. What is the potential across O and C now? Like, let's call C dash. If you go from O to C dash from this path,
KVL.
first of all, you have to find I0 first. What is I0? I0 will be how much?
E divided by R plus RS.
RS.
So what is the potential across RS? So if you go from V via this path,
Hmm.
you can get the VOC dash. You can say VO minus I0 RS equals to VC dash.
Yeah. Hmm.
So VO minus VC dash is how much?
I not RS.
But I0 itself is how much?
E by.
E by RS plus R. Yeah.
So now this turns out to be this answer.
Yes.
Yes.
And because the denominator is bigger than the numerator, so this is a fraction of E. Yes or no?
Yes.
And because it is fraction of E, it means it is less than E. Yes or no?
Yes, sir.
And because it is less than E, so it must have the null point less than L1. Yes or no?
Yes.
Yeah.
So if I say the new null point as L2, if I say new null point as L2, so for case 2, let L2 be the new null point. That is OC dash is L2. Then can we say that VOC dash is proportional to L2? Because what you balance is the potential, isn't it? Which sometimes turns out to be E, which sometimes do not turns out to be E.
Yeah.
It is clear. So I can also write ERS upon RS plus R.
Yes.
Correct. Also, we know already that E proportional to L1. So equation, if you divide 2 with 1, what you will get? E by ERS upon RS plus R equals to, and you can see we have the relation. So 1 plus R is how much? So if you know the shunt, you can get the internal resistance. Now, what is interesting is to see the numerator, which is the difference of the initial and final. So L1 minus L2 is called shift. So in literature, what they will tell you that once both switch are closed, the null point shifts by 10 centimeter. They will not tell you left or right because you have to guess whether it is left or right. So the moment you close both the switch, if K1 is closed, we know the answer is L1. If K2 is closed, the shift will be right or left.
Hello.
Yeah.
So did you ask something now?
Yes, yes. I'm asking that if K1 is closed, your null point is L1.
Yes.
If K1, K2 both are closed, the null point will shift. Right?
Yes.
The question is null point will shift left or right of original null point. Left
It will
means
be
lesser,
less than L1.
so it will shift left.
Left, huh? Yes.
So do you realize this part that shifting will
Yes.
happen on the lesser side?
Yes.
Because now you are measuring potential difference which is less than the EMF itself, right?
Yes, sir.
How many of you realize this? It's simple circuit
Got
question. This you could have solved. So you can say this is R equals to delta L by L2 into RS. Sometimes we write as shift upon new null point into shunt resistance. Let me write shunt. Okay. So have you guys realized this potentiometer?
Yes.
Yes, sir.
In fact, you could have solved directly by using the Millman's theorem, because I have told you that if we have method 2 for R, so we have E, R, RS, because I'm closing both, so I'm just representing C dash. Okay. So from Millman's theorem, if there is no potential, you can assume a potential of 0 volt. So what is the E equivalent here? E by R plus
E by R plus 0
RS,
by RS upon 1 by R plus 1 by RS.
and this is proportional to L2.
Yes.
That's it. So what you're getting E by, you can take R below, so 1 plus R by RS is proportional to L2 and E is proportional to L1. Okay. So E by 1 plus R by RS is equals to L1 by L2, which means, this is the answer. You can do in one line if you understand this Millman theorem. Is this clear, guys?
Yes, sir.
Yeah.
Yes.
So for any circuit, you can just find the E equivalent and you can write proportional to the null point which you obtain, and accordingly you can solve the question. Now, learning this is not sufficient. You need to practice first. And when you start practicing, you will find some difficulty in the very beginning. So we are going to start with SC Verma. Please open SC Verma, everyone. Current chapter. Let me also bring this. Just a minute. So you all have SC Verma ready with you?
Yes.
Yes, sir.
Okay. So question number 53. So you have to solve 53
Yes.
and 54 and 55 and 56. Just 4 questions sufficient to get your concept clear. Try slowly. Convert everything into circuit corresponding to the length and so on, and get your answer. Okay. So all the best with all 3 questions. The best way is, what is the best way? Millman's theorem. Yeah. All right. So 53 to 56 from SCV will be your practice today. And then we have a 10-minute lecture on post office box. And we are done with this chapter. So 53 to 56, how many questions? 1, 2, 3, 4. 4 questions. How many minutes? 30 minutes enough?
Okay.
So I'll be back after 30 minutes. By that time you can solve, then I'll give the solution for all 4 questions. Solve.
Or
53
2
is
done.
done. 53 done.
53, 54 done.
Very good. Anybody else?
53 done.
Great. So move slowly. It's not difficult. Just you, if you have realized that what is the circuit, how to go about the circuit, you'll find it easy. Hopefully. Okay. If you need any hint, just let me know. I'll explain the hint also. Okay, I think I should now start helping you out.
Sir, 56 doubts till 55 done.
Great. Only one question left, right?
Yeah, doing that.
Okay. 56. In 56, it is not null point. There is no null point, right? Because they're asking the current in the galvanometer, which means it is not a null point, right? So current will
Yes.
distribute here. So that's why 56 is interesting one. So we have E, we have R, and we have a potentiometer bar, and the capital this wire having resistance 15R. And we have a cell value E by 2. This is R. And it is going to touch somewhere. So let me read this question. Consider the potentiometer circuit arranged as in figure. The potentiometer wire is okay. So the length is how much? 600 centimeter, right?
600.
At what distance from the point A should the jockey touch the wire to get zero deflection? That's the first part is done. I hope so. First part we see for zero deflection, it means nothing will go from the bottom branch, right? So all
Yes.
current will be part of that. So it will be E by 16R. So it's a
Yes, yes.
K, this is I, and this is 6. Okay, we need to find that null point, right? So you can take X, whatever. So the resistance will be how much? X by 600 into that's it, 15R. So 15 by 600. No, just a minute. The fraction. Yeah, that's it. 15R. So I into R equals to E by 2. That's it. So X turns into how much? 16 into 600, 15 into 2.
320.
So that should be the answer, the first part.
Yes.
If the jockey touches the wire at 560, which is more than this, so
Yes.
it means current, the potential difference is much more than what you expected. So current will flow
Current
here.
flow.
So current will flow into this lower branch. So for that case, you can draw a separate circuit. Okay. And then just solve it. Okay. So the next part you have to draw is something like this. R. And I'll break this into two resistors. So what is the resistance up to 560? So it is 560 upon 600 into 15R.
15R, yes.
So this is 40. This is 14. So it is 14R. This is R. That's simple. And then we have another resistance, another cell E by 2. This is R. This is your simple circuit. And they're asking what is the current from the bottom one. Okay. So I can solve this in really simple way by taking this entire term one cell, second and third.
Yes.
So if you convert, this will look like E to R, then 14R, and then E by 2 and R. Do you realize this part? So basically we have three circuit in parallel, or you can say three cell in parallel.
Yeah.
So I can find the VAB, potential across the entire thing, by Millman's theorem directly. E by 2
Can use, yes.
0 by 14R and
E
E by
by
2 by R
Yes.
upon 1 by 2R, 14R, 1 by R. And this potential turns out to be E by 2R upon E by 2R. So it is E by 2, E by R actually. Upon 14R is LCM. So 2, 7, 1, 14. How much is that?
22.
Very good. So it's E by 22, right? Into 14. It's 7 E by 11. Am I right? So the net potential across A and B should be 7 E by 11, which is only possible when this will undergo charging, correct? Because only in charging we can increase the EMF, right? Because eventually what I need is, so IR is 7 by 11 into 2. This is E. 14 minus 11 is 3, no? 3.
22.
E. So the I is 3E by 22R. Because this is what they're asking, current. Can you check the answer?
Yes. Yes, it's this.
So every question, if you find difficult, think of Millman, convert into cell, reduce it, find the net EMF, and then check which cell will go charging, which will go on discharging, because the potential difference is known to you eventually. Understood?
Yeah.
Yeah, that's the answer. So this is all about potentiometer. I hope you have understood. This was a difficult one which I solved. Rest I expect you will be able to solve. If not, you can ask in doubt. Okay. So should I solve any other question? Guys, tell me.
No.
So I'll go to the next concept quickly. So the last topic. Yeah, you all can struggle a bit at home and get the answer. The last question is, oh, this is called post office box. So it is due to the reason that the earlier communication used to happen in post office, right? So we have we have to make a trunk call. You have to go to post office. Okay. So communication was not something which was happening at home. So it was happening in post office, and all the post office, or you can say universities, had the facility of this phone. So everything is started in this because post office means to communicate. Okay. So because of that reason, it's called post office box. So it's basically an instrument. And what is the purpose? That earlier we had the cable running across city. Okay. And after running across city, the cable will have a wire which is outgoing from the office, and the same wire will also incoming from the office. So we have a cable. Have you seen the telephone cable? Anyone seen the telephone cable? Oh, no one has seen. Come on.
No.
Telephone cable is a really thick one. It's a very thick. So, okay, luckily I have spent my life with telephone cable, my childhood. Because that time it was getting put inside the earth. I mean, they used to dig a big, tunnel kind of thing, and they used to put the cable to create the infrastructure. So I saw this. That time the telephone connection was, is spreading out slowly and slowly in small cities. It was earlier privilege of Mumbai and Delhi. Slowly it came to small cities, and the cable was getting spread across the city. So you can see what is happening. Okay. And in every city, we have telephone exchange. So luckily, I was living in front of telephone exchange. This cable is something very old to me. Inside this cable, you will see thousands of wire, not one, two. And it is very colorful wire. So I used to watch hours at these colorful wires and what they used to do with this. So much glue was there. If you touch, you will get some glue in your hand. So inside this cable, you have like you can say thousands of wires, maybe more than that. And wires are bundled into one part. So there are many bundles of wire, and the entire bundle is eventually packed into a big cover, and that is called cable. Okay. And this cable they put inside, because cable is like something which is having wire, then some protective layer, then some more layers, then some more layer. Eventually, it is like safer to spread across the city. And sometime due to some reason, maybe the rat, maybe the one reason, or due to some fault also, the two wires. So what is happening is we have a communication happening at post office. So the post office will lay out this cable across the city, and the wire will start from the post office, will run across the city, and will come back eventually back to the same. Okay. Now inside the cable, let's say if I'm representing only one cable which is going and coming back. So if there's a, this is short circuiting, there's some short circuiting here. So what will happen? Current will flow here, here, and here. Okay. So it will turn from here. So this entire part will not get current, correct? No current in this part. So no current means no signal. Let's say your home is here. So from this cable, we draw the wire to create a personal connection to household. So what will happen? All these phone lines will be dead because they will not get the connection. Now, can you dig the entire city to get the point where this short circuiting has happened? Is it possible to dig the entire
No.
city again? So there must be some mechanism, okay, to get this idea where this is happening. Now, these cable wires will have resistance, spread across the entire length, and therefore there is a resistance gradient. Okay, so you know that this wire will have this particular resistance gradient. Okay. So what you do exactly, you connect this end, let's call X and Y, across a device which is called post office box, and the device will give you the net resistance across this and this. So resistance means what? The resistance in which current is flowing, only this part will get the resistance, correct? So let's say the entire wire is having 100 ohm resistance, but when you're trying to calculate the resistance across X and Y, what you're getting? It's called 10 ohm. It means the current is not traveling through the entire wire, yes or no? Current is traveling lesser than the entire length. Do you realize this?
Yes.
Okay. Now let's say I know that it is 1 ohm per kilometer is the resistance gradient. So 10 ohm is, it is happening 10 kilometers away somewhere.
Yes.
So we know the blueprint of the infrastructure. We know how it is laid out in the city. So if I move 10 kilometers as per the blueprint, I can exactly get the location where this has happened. So I'll dig there itself, take the cable out. Okay. We'll do some checking, like few meters back and forth, and eventually we'll come to the right point. So there are two ways. Generally, it's very difficult process. So they have to cut the wire, entire cable, and they have to reconnect the cable and then make the safety connections and all. It's a very rigorous process. Sometimes it used to take days, not days, weeks actually. So once the phone line is dead in the old times, then it is dead for entire week, maybe for a month. Okay. So then because it's like government job. So they will go there and they'll first dig for one day. They'll pull out the cable. Then some engineers will come. They will search about the short circuiting. They will do a lot of testing and all. And I have seen this in front of my eyes happening. It is happening for months, sometime weeks and all. And the phone is dead. Okay, so that's happening all the time. So how this can be done? Okay. So generally now, because of the increasing city size and it is reaching to the small cities, villages also. So this entire cable infra is really, I mean, has spread across the entire country now. And now we don't dig, sometimes what we do is we use the, let's say in Mumbai, we have the BMC gutter. We use that gutter also. Sometimes we use the BMC pipeline also.
Yes.
Yeah, to spread this cable. Now this cable is actually leased by most of the companies for various purpose. So purpose is like, so in Mumbai we have MTNL, Mahanagar Telephone Nigam Limited, but most of the time they lease out their facility of their bandwidth. So other subscriber like Airtel, Reliance, they're not supposed to spread their own fiber. Okay, so what they do is they lease the government line and they provide the services to the consumer, but the government is not able to provide the better one. So you can understand the corruption happening at all levels. Okay. Anyway, so now what Reliance did, I mean, they spread their own fiber, optical fiber. Okay.
Yes.
To bring the 5G into picture. So Airtel and Reliance, they spread their own 5G services across the city. And as it is being laid out in smaller cities, eventually the entire country will have the optical fiber network, and then the communication will be really fast. Okay. Till that time, you have to wait. No, not you. You means in Mumbai, we are privileged. We are having facility already happening right now, but it will spread to the second tier, third tier city in coming times. Anyway, so communication is important thing. The post office box will help you. This is a device basically, which is again based on the balanced rotation bridge, and the purpose is to find the unknown resistance. That's simple purpose. Okay. So I'll leave this diagram for your context, and I'll just tell you what is this device. So it is very sensitive. Sensitive means I'll tell you why I'm saying sensitive. Sensitive. So normally this cable will have resistance over the kilometers. Okay, so you know that if you move 5 meters, the change will not be significant, right? Because 1 ohm for 1 kilometer. So you can imagine the resistance for 5 meters. It is very small. Okay, it's a fraction of a ohm, maybe the 1,000 part of
Yeah.
ohm. So measuring 1,000 part of an ohm is not feasible using meter bridge. Okay, it's totally impossible. But this is so sensitive that it can measure from micro ohm to mega ohm. That is the range of operation. So it is having ability to measure as low as possible value and as high as possible value. Both are possible with this device. So it's a very sensitive device and can measure as small as micro ohm up to, I think micro ohm is too much. I would say as milliohm up to mega ohm. Yeah. So how the device will look like? So you will have a box. Actually, it's a box. Okay? It's just like any normal box. It's a wooden box. You might have seen in your lab. So I think before I'll show you the diagram, which is meant for the understanding of circuit. Let me show you. The old post office box, the old one. Okay. Anyone has seen before post office box? No one? No
So
problem.
I've seen it.
Great. I am asking post office box. Google is saying Bollywood box office collection. What is this? Laptop is not post office. Impossible. Now Google has failed. Finally. Hopefully you can see now. Can you see now?
Yes, sir.
Yes.
So now you can see that there, look at the topmost line, 10, 100,000, again 10, 100,000. It's a repetition, right? You can see there's a repetition of 10, 100,000 on both sides. Okay.
Mhm.
And then below, you can see it starts from 1 ohm. This is 1 means 1 ohm actually. So 1 ohm up to 4,000. It can go up to 5,000 also. And then you can see some keys actually. These are called keys. Okay. So what exactly the keys will do? So this is a metallic strip. Oh, there's a key for infinity also. You can see if you pull this, the resistance will be infinite. It will like breaking the circuit. So this is the actual circuit which you need to know. Okay. So this part, let me annotate. Yeah. This part and this part is called a ratio arm. I'll draw the circuit. You understand what is, and the entire rest of the part from here up to this entire value. This is called resistance arm. It means you can choose. So what will happen? Let's say you start the circuit and current enters from some of the end. So let's say current will enter from somewhere here. Imagine, okay, somewhere. So I have something to enter current and will exit. So once current will enter, what will happen? It will flow through these metallic strip. So what is the resistance offered to the current? 0, because metal will offer no resistance. Are you getting this point?
Yes.
What if I pull this? So current will go here and there is no way to go forward. It has to go through the wiring done below actually. So there is a wiring below. It will go through this wire, then it will come here. It is inside the box, which you don't see. So that will offer 100 ohm resistance. So now this current will face how much resistance? 100 ohm resistance. So now it will come here and then it will move like this without any resistance further. But suddenly you pull this resistor, then current will come here and will go through the below and will come back here. Now what is the resistance it is facing?
3,000.
3,000. And here 1,000. So it's like it will face 4,000 resistance. So every key which you pull will add resistance to the circuit. Understood? So imagine if you pull all resistor from 1 to 4,000, how much it will become? 1, 2, 3, 3, 6, 4, 10, 20, 20, then 20, 40, 70, 110, 210, 410, then 710,
7.
then how much? 1110,
Well,
then 2110, 4110,
One.
something 7,000 and
410.
roughly 10,000, right? More than 10,000, 11,000.
11,000.
That much resistance we can create, 11,000. Okay. And the minimum we can create is 1 ohm. Correct? So this is 1 ohm. If I pull only this one, I can create 1 ohm. Do you realize this? Yes or no?
Yes.
Yes,
So
sir.
just keep this diagram in your mind. Let me draw the actual diagram. Okay, not actual. This is the actual. I will draw the circuit diagram. Okay. So let me go back to my circuit. It is very sensitive device. How we draw? We draw like this. Let me draw this. So this is the top strip, metallic strip. So what you are seeing is the top view, okay?
Yeah.
And to represent key, what I'll do is I'll make it something like this. One gap, two gap, three gap. On this side, I'll leave the center. It's like a center. And then on this other side, I'll again make gap, 1, 2, 3. That's it. So this is the gap on the left and right, and the value is 10 ohm. I can choose anyway. No, that's totally okay. Same 10 ohm. You can say A, B, C. That's it. The remaining part I can draw again. I have to draw many holes. 1, 2, 3, whatever. I mean, it doesn't matter how many count. Just the idea is important. Okay. Okay. So I'll put this as capital D. This is the last one because we have to convert this into 3 parts. How to convert this into circuit? So look at the circuit part. So A to B, we draw like this. A, B, and then draw B to C. Okay. This is called R1. This is called R2. Oh, just a minute. R1. So the ratio arm will represent by symbol R1, R2. Then the D, A to D, this entire thing will offer you some resistance depending on how many keys you pull. So the D comes here. This is called R. So which pointers are left? C and D, right? So this C and D will get connected here, you know, where the X and Y. Do you realize this what I'm saying?
Yes.
So this C and D will connect to something unknown, and this unknown will be represented by a symbol X. Understood? Now to convert this into balanced V-twisted bridge, you need to supply some power. So power will be supplied across which two terminal? A and C. Do you realize this?
Yes.
And the galvanometer will be put across which two terminal? Which two end? Because for null deflection, or you can say for balanced V-twisted bridge, okay, it works on the principle of balanced V-twisted bridge. So what they will ask you in the examination? Very simple question. Between which two point unknown resistance is connected? What is the answer? They'll give you the left one.
C and D.
They'll ask you between which two point you are going to connect the unknown resistance. The answer is C and D. Okay. Between which two point we connect the power supply? Power supply will be
B.
power supply is between which two point?
A and C.
A and C.
Ah,
And between
Yes,
which two
yes.
point you connect? Between which two point you connect the galvanometer?
B and D.
You're done. This is a J advanced point. So G are simple question. Find the point between which the unknown is connected. Over. That's it. Now for balance condition, what you can write? R1 x equals to R1 R2 RR2, like cross product
Yes.
or whatever you want. So what is x? R2 by R1 into R. That is why R1 R2 is called ratio arm. So R1 and R2. Okay, R called ratio arm. And now you know the remaining AD is called resistance arm. And what you can do, depending on the, let's say if I pull the plug of 10 ohm on the R2 side, if I pull this plug in this one, and 1000 from this side, this is 1000. What is the ratio now? The ratio is how much? 10 from the right and 1000 from the left. What is the ratio of R2 by R1? 1 by 100.
Yes.
And if I choose R equals to 1 ohm, what is the minimum unknown we can measure? 0.01 ohm, isn't it? 0.01 ohm. Do you realize this? What I'm saying? If I plug R2 of 10 ohm value, if I plug R1 of 1000 ohm value, the R2 by R1 becomes 1 by 100.
Yes.
And if I plug from the remaining part only 1 ohm, then R is 1 ohm. So X is how much?
0.0.
0.01.
Yes.
So you can imagine that you can actually measure 0.01 ohm using post office box, which is not possible with meter bridge. Because in meter bridge, the error is that much, more than that. Do you remember?
Yeah.
In meter bridge, the error is more than that. Okay. So that's why for very small or very large resistance, we never use meter bridge. Meter bridge is used for the moderate value of resistance, but the post office box is really powerful device. It can measure any value. What you are supposed to know? This circuit and how to convert this entire diagram into this circuit, and then you can answer every question that JEE has asked. Okay, and with this, we complete the current and electricity. Okay, and the next lecture will be your
Magnetism.
magnetism. So this is really simple chapter called magnetism. So before you start reading the magnetism, go and revise cross product from vector lecture, because we are going to use cross product very often. So this chapter will be very easy for many and very difficult for many. Let me tell you which kind of difficulty you will face. Many feel direction as a difficult quantity to visualize. So direction is something which you have to mentally create in 3D. If you are that kind of guy who can understand the direction mentally, this chapter is piece of cake. If not, then for you, the only way to understand magnetism is through mathematical formula. So you have to stick to I, J, K, write properly, get the answer, and try to understand through the mathematical, or you can say analytically. So just practice cross product, try to understand the meaning of it. And I think vector lecture is there. If you want, you can watch vectors. I'll share the link again. This was the last 2-3 lectures of cross, where we have done a lot of practice of cross product. And if you do so, you will find the chapter really easy. It's like nothing. I mean, it is all about direction. The rest is you can do mentally. There are very limited formulas in this chapter, 3-4 formulas. Very easy to remember formula and very easy to apply as well. Okay. So you will see is not easy one, of course, because since I'm going to teach you this chapter, so I'll make sure it's not very easy. So you'll see some really challenging problem. And I can also assure you that most of the question of JEE Advanced will come from my notes only. If something goes beyond this, your fee will be returned back. So stick to my notes for this chapter. Read, derive, revise from notes. That's it. Because I'm going to cover every possible question in great detail. Okay. So see you in the next lecture.
Sir, I had a doubt in rotation.
You can ask.